Welcome to my presentation on Attention is All You Need, a groundbreaking paper that introduced the transformer model. This revolutionary architect relies entirely on attention mechanism, doing away with recurrence and convolution in sequence transduction tasks. Recurrence and sequence transduction uses a traditional model like RNNs, recurrent neural networks, that process sequence data step by step, maintaining a hidden state that gets updated at each step. This recurrent nature allows the model to handle variable length sequences, but can struggle with long-range dependencies and is inherently sequential, limiting parallelization. Convolution in sequence transduction uses convolution neural networks, or CNNs, that apply filters over the input sequence to capture local patterns. Why they can use parallelization more easily than RNNs can, they typically require deep structures to capture long-range dependencies. Attention mechanisms are a technique that allows the model to focus on different parts of the input when producing each part of the output. It's like how we focus on specific words when understanding or translating a sentence. In the transformer, this mechanism allows the model to weigh the importance of different words in the input sequence when generating each word in the output sequence. The transformer model replaces these recurring convolution operations with self-attention, allowing it to capture global dependencies more directly and enabling more parallelizations. This innovation led to significant improvements in various sequence transduction tasks, particularly in machine translation. The transformer brought several key innovations to the field. As this comparison shows, unlike traditional RNN or CNN models, the transformer uses self-attention mechanisms throughout. I stated this in my introduction. This allowed for significantly more parallelizations and achieved state-of-the-art results in translation tasks. So let's dive into the transformer architecture itself. As you can see here, it consists of an encoder and a decoder, each composed of 6 identical layers. The key components are the multi-head self-attention mechanisms and position-wise feed-forward networks. This design allows the model to process input sequences in parallel, greatly speeding up the training and the inferences. At the heart of the transformer is its attention mechanism. This diagram illustrates the scaled dot product attention and how it's used in multi-head attention. This allows the model to focus on different parts of the input when producing each part of the output, greatly enhancing its ability to handle long-range dependencies. Since a transformer doesn't use recurrence, it needs another way to understand the order of input sequences. This is achieved through positional encoding. This is represented by the sine and cosine waves of different frequencies. This clever technique allows the model to inject information about the relative or absolute position of tokens in the sequence. The transformer was trained using a custom learning rate schedule shown in this graph. The learning rate first linearly increases during a warm-up phase that you can see, then decreases proportionally to the inverse square root of the step number. This schedule, along with the atom optimizer and techniques like residual dropout and label smoothing, was crucial for effective training. The results were extremely impressive. As this chart shows, the transformer outperformed previous state-of-the-art models on the WMT 2014 English to German and English to French translation tasks. The large transformer model achieved a BLEU or BLEU score of 28.4 on the EN to DE and the 41.8 on the EN to FR, or English to French conversion, setting new benchmarks in the field. The transformer's capability extend beyond translation. When applied to English constituency parsing, it achieved impressive results without task-specific tuning. This table shows how the transformer compared to other models, achieving state-of-the-art performance, especially in semi-supervised settings. One of the key advantages of self-attention is the reduced path length between any two inputs and the output positions. As this diagram shows, while RNN having a linear path length, self-attention provides constant length paths. The heat map visualization here shows how the model attends to different parts of the input, providing insight into its decision-making process. The researchers explored various model configurations. These charts show how performance varied with changes in the number of attention heads, key value dimensions, model dimensions, and feed-forward layer sizes. These experiments helped in understanding the model's behavior and in finding the optimal configuration. In conclusion, the transformer represented a significant leap in natural language processing. This infograph summarizes its key achievements: state-of-the-art performance, improved efficiency, better handling of long-range dependencies, and high generalization capabilities. The transformer's success has led to its widespread adoption and inspired numerous subsequent models. Looking ahead, the potential applications of the transformer architect are vast. Ongoing research is exploring local attention mechanisms, non-sequential generations, and adaptation of different modalities, promising exciting developments in the field of AI and machine learning.